Universidad de los Andes is located in the historic district of Bogotá, and this place is under a huge project of renewal called Progresa Fenicia. The axis of this project is a water channel called environmental axis, which goes across a little park called Espinosa Park. Having in mind the intention of offering new spaces for the students and the sector, the university is developing a project called Centro Cívico Universitario, which means University Civic Center.
Un aspecto importante de este edificio es que es la cara urbana de la universidad. Al estar con su fachada principal sobre el Parque Espinosa, este es el primer edificio del campus central de la universidad que realmente tiene fachada urbana, que es visible desde el eje ambiental y en ese sentido tiene el reto de convertirse en la fachada principal, la cara de la universidad.
Not only for the architect this project is important. The project manager explained that we are constructing not only one building, we are constructing the entire campus.
El segundo componente importante para el desarrollo del proyecto fue, como lo dice su nombre, que es un centro cívico universitario, lo cual quiere decir que ese proyecto está pensado para invitar a los ciudadanos a entrar a la universidad. Para ese efecto va a tener un teatro, va a tener una biblioteca, va a tener una sala de exposiciones que van a estar a disposición de la ciudadanía en general.
As research group, we have the figure of BIM managers, and we create the BIM execution plan. For the Synchro challenge, we include the fourth dimension using Synchro. In the web, we divide the project in systems, and we use it for the Synchro challenge, including always logistics and safety.
This year, we wanted to give a little bit more detail to the different construction phases. So first, we obtained a conceptual model of surrounding buildings, and we located our project geographically. Then, we built a Revit model that included special items for demolition. Once we imported the Revit model into Synchro, we could establish the demolition sequence and the different zones. Also, using lean construction and location-based management, we could define the production units, which were balanced, in order to achieve continuous flow of work. In the same way, we used Synchro to identify dangerous areas and evaluate the best alternatives to provide a safe construction site.
The foundation design is based on footings, foundation beams, and retaining walls. The excavation and foundation process proposed starts digging pits on the same width of the retaining walls. Once the pit is dug, concrete is poured immediately to create barrettes. When all the barrettes are poured and a complete retaining wall is done, the excavation process begins to remove land until a little bit less than 12 meters below level zero. This process was proposed with brigades of excavators and bobcat mini excavators. When the foundation level is achieved, a manual excavation is proposed to dig the footings and foundation beams places.
The structure is composed by a concrete frame with a beam girder floor system. Based in lean construction principles, we look for a constant flow, dividing each floor in similar cycles, always looking for managing the production and the use of resources as the form works.
We try to generate a detailed information model of the structure, so we model the shores, formworks, slab sliding, security and safety elements. This was done with Revit's Dynamo visual programming due to its efficiency, and we start realizing which of the cycles are going to be the more complex on site. While making this model, the 3D space was full of resources and equipment overlapped that were not easily understandable or useful. This model makes no sense without 4D, so this is where we use the cycle and activity parameter that we use in the structural frame. We can easily change the order of the cycles by adjusting the parameter in Revit, and Synchro would just replace the resources of the task. Thanks to the 4 dimension, we can manage properly time and space in the site and generate more accurate resources plan. After the shores are removed, we plan the architectural finishes following a simple baseline that parameterizes the task resources by level, family, or type of the element. Activities were according to the categories, maintaining accurate relations and avoiding overlapping and maintaining a constant flow.
Regarding the special buildings component, we kept in mind the unifying role of the CCU at the university campus. This was reflected with the inclusion of 2 external structures, underpass and overpass, to guarantee the connectivity with the west side. In accordance with the previous idea, both pathways were included at the same schedule abreast with the building's vertical growth. The tunnel was incorporated after the basement columns and the bridge after the fourth level foundation. The tunnel's construction methodology included 3 key activities: steel assembly and concrete pouring, followed by soil removal, and the assembly of an asphalt layer. On the other hand, the overpass construction began with the assembly of the superstructure, prominent beams, bracels, metal framework, and steel decks, chased by roofs and glass installation.
With Synchro, we achieved a complete visualization of a lean schedule, including safety, zones, trades, equipment, and logistics. We are convinced that Synchro, together with collaborative planning, guarantee a high productivity and performance in construction.